Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. Every day we hear sounds from across the room, from out of doors, when our friends communicate with us, and when we hear our own voice. In this video, we'll learn about these acoustic waves. These are spherical waves.
So let's get started. We will first summarize what we've learned so far about harmonic wave propagation. We found that the general solution of plane wave propagation in one dimension x is the acoustic pressure is a function of x and t, and it's equal to one function called f1 that has argument ct minus x, and this referred to a positive x propagating wave, plus another function f2 with argument ct plus x, and this was a negative x propagating wave. These waves are called plane waves, and harmonic plane waves in an infinite duct, written out in the complex exponential form, would be p underline, denoting complex when we write it out by hand. It's a function of x and t, and it is equal to a complex amplitude a multiplied by the complex exponential e to the j omega t minus kx. That corresponds to the same function above, which was f1. And then we'll write out the second part, the leftward or negative x propagating wave. We'll call this complex amplitude b, e to the j omega t plus kx. Now, we found before that the general solution for spherical wave propagation was the acoustic pressure is a function of r in t, where r is the radial dimension, and it was equal to 1 divided by r multiplied by some unknown function f1 with argument ct minus r. So by analogy to plane waves, harmonic spherical waves we find to be written as complex amplitude p, which are a function of r and t, and we see the analogy here so that we'll have this complex amplitude a, but it's now divided by r. The complex exponential remains the same, excepting the substitution between x and r. So it is e to the j omega t minus kr. One thing that's important to note here for harmonic spherical waves, a amplitude has units of pascals meters in order so that our acoustic pressure has units pascals once we divide through by the r in the denominator. So let's examine this further in terms of spherical wave particle velocity. Euler's equation for spherical coordinates is given here. In the one dimension of r in spherical coordinates, it looks quite similar to the Euler's equation in one dimension x. So we have minus del p del r is equal to rho naught, the atmospheric density, multiplied by del u del t. Now, given that our acoustic pressure form is written as we found it on the prior slide, complex amplitude p, or complex pressure p, is a function of r and t, is equal to complex amplitude a on r, and then multiplied by e to the j omega t minus kr. The particle velocity we find for spherical waves, applying this to Euler's equation, is given to be complex u as a function of r and t is firstly multiplied by quantity 1 minus j on 1 on kr, or k is our wave number, and this quantity in brackets is multiplied by the harmonic acoustic pressure p of r and t divided by rho naught c. So let's recall acoustic pressure and particle velocity for both plane waves and spherical waves to kind of gather our understanding here. So recall for plane waves that we have complex acoustic pressure p as a function of x and t is equal to complex amplitude a, e to the j omega t minus kx. And we won't write out the term corresponding to negative x propagation. We'll leave it at that for this example. The complex particle velocity in one dimension, u as a function of x and t, is the acoustic pressure, p, as a function of x and t, divided by rho naught c. Now for spherical waves, what we have here is p as a function of R and T is complex amplitude A on R, e to the j omega t minus kr. Whereas for U, we have U as a function of R and T is 1 minus j on multiplied by 1 on kr multiplied by the complex acoustic pressure of R and T divided by rho naught C. So what we see here when we compare spherical harmonic waves against plane harmonic waves is that the particle velocity is no longer in phase with acoustic pressure. And this is seen by the fact that for plane waves, there are no complex terms pre-multiplied by the acoustic pressure for particle velocity. Instead, the particle velocity is directly proportional to the acoustic pressure for one-dimensional plane waves. But for spherical waves, what we have is that there is a complex term multiplied by the acoustic pressure, indicating there is a phase difference between acoustic pressure and particle velocity for spherical waves. Let's introduce another acoustic quantity that's especially relevant for spherical waves. This is called the acoustic intensity. So we haven't introduced energy metrics yet, but it's safe to assume, and it's important to know, that acoustic energy transmits when waves propagate, and the acoustic intensity quantifies this energy transmission. In general, acoustic intensity, which we'll denote as capital I, is a vector, and that's why we use this overbar notation. It's a time average of the real component of acoustic pressure multiplied by the real component of particle velocity. The units when we work this out are watts per meter squared, so it's an energy quantity, specifically energy per area. For one-dimensional harmonic waves, whether they're plane or spherical, the acoustic intensity, we can lose its vector notation due to the one-dimensionality, and it's identically equal to P RMS squared divided by rho naught C, which is also equal to amplitude P squared divided by 2 rho naught C. So this capital P is the amplitude of the complex acoustic pressure, and the PRMS is amplitude divided by square root of 2. It's important to recognize that even though both plane and spherical wave acoustic intensity is computed by this formula shown here on the right, the interpretation is different. For plane waves, I is independent of X. This is because the acoustic pressure does not depend, the acoustic pressure amplitude does not depend on X. But for spherical waves, I is proportional to 1 on R squared. This is because the amplitude, capital P, is inversely proportional to R, so that intensity, which is proportional to P squared, is then proportional to 1 on R squared. So for plane waves, acoustic intensity does not change with change of X. But for spherical waves, acoustic intensity reduces quickly with increase in R. Another important energy quantity exists in acoustics, and that's called acoustic power. It's an integration of acoustic intensity around the surface that encloses the source of acoustic waves. The units of acoustic power are watts, so this is our power. For one-dimensional plane waves, considering the duct, that area is really just the duct cross-section, so this is our S. That's used in the integral. When we have spherical waves, let's say our source, this box, generates sound. It's generating sound, and this box is kind of suspended somehow in the air. The area that we need to consider is the sphere that encloses this box. So here the S is equal to 4 pi R squared, where R is some radius from the center of the box to that spherical location. If the intensity is everywhere the same, this acoustic power integral simplifies greatly. So if we're far enough away from the source, in the example on the right for spherical waves, the S is identically equal to 4 pi r squared. If we're very close to the source that's generating acoustic energy, it's difficult to measure sound power very accurately. But a few things need to be recognized. So for plane waves, acoustic power is independent of X. And we know this because acoustic intensity is independent of X for plane waves as well. But for spherical waves, power is also independent of R. And this is because I is proportional to 1 on R squared, and here S is proportional to R squared. So this means power, or acoustic power, is a source characteristic. Let's summarize these relations for plane and spherical waves in a table. We'll have one column of relations for plane waves and another column for relations of spherical waves. Let's begin by expressing our relations for acoustic pressure. Harmonic plane wave acoustic pressure is complex P as a function of x and t is equal to complex amplitude A multiplied by e to the j omega t minus kx. We'll neglect the negative x propagating wave for now. The harmonic spherical wave acoustic pressure is a function of r and t, and our amplitude is complex amplitude A divided by r multiplied by e to the j omega t minus kr. The particle velocity is next. The particle velocity for harmonic plane waves is u as a function of x and t is equal to the complex acoustic pressure as a function of x and t divided by rho naught c. Whereas for spherical waves, u is a function of r and t and is equal to a set of coefficients 1 minus j multiplied by 1 on kr, where k is the wave number. Those coefficients are multiplied by the complex acoustic pressure, p is a function of r and t, divided by rho naught c. So here's where we see, again, that acoustic pressure and particle velocity are in phase for plane waves, but they are in general not in phase for spherical waves. Let's then find exactly what the acoustic intensity is for plane waves. We recall that the acoustic intensity is capital I, and that's equal to the amplitude of acoustic pressure P squared divided by 2 rho naught C. So if we substitute our amplitude in from the harmonic plane wave expression, we've got the complex amplitude A squared divided by 2 rho naught C. Let's do the same for spherical waves. The first part of this equation is the same. It's still capital P squared divided by 2 rho naught C. But when we substitute that in, we find once again we have complex amplitude A squared in the numerator, but in the denominator we have 2 rho naught C r squared. This demonstrates clearly how the acoustic intensity for spherical waves reduces quickly for increase in r. Let's finally write the expressions for acoustic power. The acoustic power is the product of acoustic intensity and the area. And in this case, if the area is S of the cross-section of a duct, what we have is the complex amplitude A squared times S divided by 2 rho naught C. For spherical waves, we have, after simplification, 2 pi complex amplitude A squared divided by rho naught C. For plane waves and spherical waves, the acoustic power is independent of evaluation location. In other words, it's independent of where we place microphones to measure acoustic pressure.
That's it for this video. In the next video, we'll learn how to characterize these acoustic waves in terms of sound levels.